At CERN's LHCb experiment, a single collision produces four particles: a kaon, a pion, a positive muon, and a negative muon. On their own, none of these particles are unusual. Unstable particles break apart inside the Large Hadron Collider by the billions. But when physicists compare the directions these four tracks take against the predictions of the standard model, averaged over enormous numbers of these events, the pattern does not match. That mismatch first appeared in 2013. More than a decade of additional data, tighter analysis, and repeated scrutiny have not made it go away. The particle responsible is called a B0 meson, and it survives only a fraction of a second before decaying. In this particular decay, it produces a K*0 meson along with the muon pair. The K*0 then splits into the kaon and the pion. What's left is four charged particles moving outward from the same point, and the LHCb detector tracks exactly where each one goes. Those four tracks carry more information than their existence alone. Their energies, their directions, and the angles between them are all predicted by the standard model. Not perfectly, since the strong force makes part of this calculation genuinely difficult, but precisely enough that a real disagreement should stand out. This decay is useful for a specific reason. The standard model has no direct route for it. A bottom quark turning into a strange quark while producing a muon and an antimuon can only happen through a quantum loop involving particles that never actually appear in the collision. That makes the decay rare, and it makes it sensitive. Any undiscovered particle heavy enough to enter that loop could shift how often the decay happens, how the muons share their energy, or which directions the final particles favor, without ever showing up directly in the detector. LHCb does not test this by measuring a single angle against a single number. The collaboration reconstructs the complete geometry of each decay, sorts events by the energy carried by the muon pair, and studies how the four particles are distributed across three separate angles. From that data, they build several quantities engineered to expose small deviations while canceling out some of the largest theoretical uncertainties. One of them, called P5', is where the disagreement first showed up and where it has stayed. In 2013, LHCb reported that part of this angular pattern didn't match the standard model prediction. The deviation wasn't large enough to call a discovery. It could have been statistical chance, an underestimated theoretical uncertainty, or an overlooked strong force effect. So the collaboration kept collecting data. The deviation didn't go away. That left two competing explanations. Either an undiscovered particle is interfering with the decay, or the standard model calculation itself is missing part of the physics already contained in it. Distinguishing between those two possibilities is exactly what the latest analysis was built to do. This newest LHCb result draws on years of proton collision data recorded across multiple LHC runs, and it is a substantially more detailed analysis than the original 2013 measurement. The team modeled the full motion of the kaon-pion system rather than treating it as a simplified object, accounted for the muon's mass, divided the data into narrower energy bins, and measured the decay rate and the angular pattern together rather than separately. They cross-checked the result using two independently developed analysis frameworks, rejected mismatched particle combinations, removed known decays that could mimic the signal, and used control samples to correct for differences between real data and simulation. The angular pattern still didn't settle onto the standard model prediction. In two neighboring energy ranges, P5' differs from the standard model calculation by 2.6 and 2.7 standard deviations. A related angular quantity shows similar tension, and the decay itself continues to happen less often than predicted across a significant part of the dataset. On their own, deviations of 2 to 3 standard deviations aren't unusual, and most of them don't survive scrutiny. A well-known anomaly in a related B Meson decay, a difference in how often it produced electrons versus muons, looked significant for years before a more precise 2022 measurement showed it agreeing with the standard model after all. That history is exactly why this result can't be called a discovery. What makes it harder to dismiss is how it has held up. This isn't a new bump that showed up in the latest dataset. It's the same discrepancy that has survived more than a decade of growing statistics, more careful modeling, and progressively narrower energy bins. When physicists translate the full angular dataset into a single theoretical parameter, a quantity called C9 that governs the strength of this particular quantum loop, the standard model value is disfavored by 3.6 to 3.8 standard deviations, depending on which theoretical calculation is used. Including the lower than expected decay rate pushes that figure to roughly 4 standard deviations. 4 standard deviations is significant, and it is also short of 5, which is the threshold particle physicists use before calling something a discovery. Even at 5, they would want an independent measurement to confirm it. So this remains a persistent discrepancy, not proof of new physics. The more dramatic explanation is that an undiscovered heavy particle is contributing to the same quantum loop that drives this decay, shifting the effective value of C9. That could be a new force-carrying particle, or something that connects quarks to muons in a way the standard model doesn't allow. Such a particle would never appear as a track in the detector. It would only show up as a change in the odds behind the tracks that do. The more conventional explanation involves the strong force. Short-lived particles containing charm quarks can form briefly during the decay and affect the muons that come out the other side. Calculating their exact contribution is extremely difficult, and if physicists have underestimated it, that alone could push the angular pattern away from the clean standard model prediction and mimic the signature of new physics. LHCb has run dedicated studies looking for exactly this effect. So far, they haven't found evidence that it's large enough to fully explain the discrepancy, but they haven't ruled it out either. The latest analysis also compared B0 mesons with their antimatter counterparts, looking for differences that would point to CP violation. Those differences came out consistent with 0. The standard model isn't failing across every part of this decay. The disagreement shows up specifically in the angular pattern and the decay rate, not in any matter-antimatter asymmetry. That selectivity is useful because detector problems and mismodeled backgrounds tend to show up in more than one place at once. Here, most measurements behave exactly as predicted, while one specific family of angular observables keeps landing away from the standard model. That doesn't prove the effect is new physics, but it rules out some of the easiest mundane explanations. The next step is more data from LHCb's upgraded detector. A larger dataset won't just shrink the error bars, it will show how the discrepancy changes across different muon pair energies. And new physics is expected to produce a different energy dependence than a strong force effect would. That difference in shape is what should eventually settle the question. It's possible this anomaly still resolves into an ordinary, if extremely difficult, standard model calculation that hasn't yet been done precisely enough. It's also possible that with more data, the same deviation returns with smaller uncertainty and a shape that conventional strong force effects can't reproduce. Right now, more than 10 years after it was first observed, the pattern is still there, and nobody has been able to explain it away. There are a few books in the description if you want to go deeper into the kind of physics we explore on this channel. And if you want to keep going right now, there are 2 videos on the end screen that connect with the bigger questions we keep coming back to here. Thanks for watching. See you in the next one.